In the previous video I showed this tool. It's a piece of software I'm working on to simulate the HP NANO processor, and in particular I'm trying to repair an HP 9845B vintage computer, and the thermal printer in that machine contains one of these processors, and something I've wanted to do for a number of years was to create a nano processor simulator, and that's what this software is for. I very briefly introduced it in the previous video, but in this video I want to go a bit further and see if it can actually process data that's fed to it and output some printer data. And the reason for doing that is this is not a simulation of outcome. This is a simulation of the inner workings of the nano processor and the printer. So it's a kind of a bit by bit simulation. So if this is working correctly, then it should be able to execute the code that's in the ROM in the HP printer, and it should be able to output some printer characters. So before we try running this, a few changes I've made and a bit more work I've done on this to make it more fully compliant and the same as the actual hardware that runs in the machine itself. So the first thing is we'll look at the schematic, and I just want to explain a couple of these circuits that I've simulated in the software. And one thing to bear in mind is the presence of this IC. It's IC 17. I'll just zoom in so we can see this a little bit more clearly. So this device is a bidirectional binary buffer. It's also a level shifter, so it shifts levels between TTL, which is what we have on the main data bus in this printer, and the MOS level signals that go into the nano processor itself. But one of the things that makes this project a bit more complex is this buffer also inverts the data. So any data coming out, any data going in is inverted. And we need to take that into account when we are developing the simulator. And we can't just make the assumption that data going out is also inverted when it comes in. So for example, we've got the nano processor at the top just off the screen. The data from it comes out of its data bus through this buffer onto the main data bus on the board. And if we want to store data in the RAM through these two devices over here, the data is of course inverted, but we can't just make the assumption that when we read it back it's inverted again, so we end up with what we started with. As I'm going to demonstrate and explain in this video, the data from the RAM also can go directly to these shift registers, in which case it's not inverted. So whether the data stored in the RAM is inverted or not inverted depends on where it comes from and where it's going. And of course, if the nano processor reads the data back out of the RAM, it is inverted, and so we need to be mindful of that when we are looking at the data. The test connector, if I scroll across to the right, we've got this test connector down the right hand side of the schematic. The pins on that connector are connected directly to the data pins on the nano processor. So they will not be inverted. So we need to again make sure that we keep that in mind when we're looking at data if we capture that on the logic analyzer. Also, if we scroll up to the nano processor itself, the test connector pins are these pins along the top as well, and they're on the output of the buffer that is attached to the address bus of the processor, and these invert the data as well. But the test connector is on the outside of these buffers, not the inside. So we need to remember that the address is inverted. So if you are trying to disassemble this, then the bytes need to be reversed, not inverted, just the order reversed that they appear in the data. Okay, so again, we need to take all this into account when we create the simulator. So one circuit I want to explain fairly briefly, but it's quite a clever circuit, and It's one that we do really need to simulate in the software, so I thought I would briefly explain how this works, because on first sight it can look a bit unusual. So this is the data to serial stream converter. All the data going to the print head goes out of this pin, so it goes out as a serial data stream, but it comes out of these shift registers. It might appear that it's coming out of the processor, but it's not. Just bear in mind these direct output pins on the processor are bidirectional, so if the Nano processor enables one of these pins and tries to set it high, it does that through a current source, and it's quite a low current that is provided to pull that pin high, but it means that an external device can pull the pin low, and the Nano processor can also read that value in. So external devices, as long as they're open collector, as this gate here is, can interact with these direct output input lines, and so the Nano processor can use these as bidirectional lines. So as I said, this circuit's quite clever. The general principle is similar to the character ROM in a CRT system. So the data values, so for example we use an uppercase A, which is 41 hex, that's actually sent directly from the Nano processor, or it may come from the RAM chips. It might be stored in RAM down here, but it has to get into the character ROM as an address. We can't feed that directly out into the data stream because it would be the wrong value. So as with a CRT character ROM, each character is made up of a number of separate bytes that create a bitmap image of that character, and they are used in turn as each line of the display is scanned. Each character is selected based on the current character in that scan line position, and the current byte within the bitmap is selected using the lower 3 bits of the address, which in this case are controlled by the Nano processor. This system's a bit more complex than most, in as much as the Nano processor doesn't actually scan the lines in order, so it doesn't go through from 0 to 7 as a CRT system normally would. It scans them out of sequence, and also it may repeat certain lines, and it does that so it can extend characters. It can print them at 1.5 times normal size, but it also allows it to have a couple of lines of pixels beneath the main body of the character for tails in Y's and G's, that sort of thing, or above the character. And it does make it look a bit confusing when you're trying to look at this on a logic analyzer, because the addresses don't appear in the sequence you might expect. Also, it might seem a bit strange having the data out going into the data in lines of the shift registers, and then the data outlines of the shift registers also going into the address inputs of the character ROM. But it makes sense when you realize that this parallel load line is controlled from the Nano itself. So the way this works is we've got the in-out decoder circuits over here, and that allows the Nano processor to send control pulses to either the RAM or the clock input of the shift registers. So if it wants to load data into the shift registers, it lowers this line, and that puts the shift register into a mode where really the shift register itself is disabled, and this just then acts as 4 D-type flip-flops. The daisy chained, so it acts then like an 8-bit D-type flip-flop. And then whenever a clock pulse is applied, whatever data is on the inputs makes its way through and is latched to the outputs. Does that on the rising edge of the clock. On the falling edge of the signal that generates this, we might either select the ROM by taking the STM line low, and then data coming out of the data pins of the ROM can then be latched into the shift register on the rising edge of the clock. Or we might select the RAM chips, in which case the RAM would then output data when the chip enabled line goes low, and then on the rising edge of the clock, the data clocked into the shift register is whatever happens to be on the data bus, in this case from the RAM. We can also send data directly from the Nano processor, albeit it will be inverted. As long as the Nano processor takes that into account, it will be fine. But this means that we can use these two shift registers as latches to send an address to the character ROM. We can also use it to act as a shift register for the actual data. So when we run the simulator, you'll notice that it goes through two steps each time it wants to get a byte from the character ROM. It will first send an address, which is really the character value, through to the address lines of the character ROM. Depending on the row that's being scanned, the three lines from A0 to A2 will be set up to select the appropriate byte within that bitmap within the ROM. And then when it wants to get the data from the ROM, it lowers the STM line, toggles that data in to the shift register, and then the parallel line can go high. Any subsequent clock cycles that the shift register receives after that will simply shift the data out through the least significant bit of the shift register. So a very clever system. They've made a lot of use of a few components to get a very powerful, very fast and very flexible system where they can get data either from the character generator ROM or from the RAM or from the Nano processor. The inversion of data coming out of the Nano processor also has other impacts, of course. When we load the timer for the interrupt, we have to bear that in mind. Now it works out fairly well. This timer increments with each clock pulse, so if the Nano processor outputs a value of 2 because it wants to count 2 cycles, that will be inverted. We'll get FD being fed into the timer, and 2 clock pulses after that we'll get the carry out and we'll get the interrupt, so it works out quite well. We need to bear in mind data we see in the RAM will be the inverse of what the Nano processor put out, but it's true data as far as the shift register is concerned. Same with the address select register for the RAM. Anything we send out of the Nano processor will be inverted, and the same with data coming in from the HP 9845. That will be inverted as it goes through the buffer, as will the status information. So we need to take all that into account as we write our software. So going back to the simulator, we can load a file, and this is again the output of the disassembler, and also the software will load this image file. This is the binary image file for the character generator ROM on the printer control board, and that's loaded into an array internally in the software, and that's so that we can use the character set from the ROM directly in our software simulation. That's loaded whenever we load a new file. So we'll load the file. We've got the source code as we had before in the panel on the left. What we have to do now when we try and run this is set it up such that it simulates what the hardware is doing. So the device input 1 is really the status information coming from the HP 9845. So that is the data coming through these devices, and these are fed from the both the switches on the printer, but also from the decoded pins inputs from the HP 45 itself, so the register select pins, and that allows the HP 45 to inform the printer that there is some valid data on the data input. So in this case we want to set this up with 112, and that just sets the bit values to the state they're in when the printer is idle. And what we can now do is we'll run through to the first interrupt. I'll speed this up so it's running at fairly high speed, and you'll see the system will initialize, it loads some values into the RAM, and then we'll get through to the idle loop in the software. So I'll run it through to that point now. So this is really what we were doing in the previous video. Notice we're waiting for the interrupt to time out. I've now got this 10 times speed checkbox, so we'll speed this up a bit. It's now run through, and we've run through to the first interrupt. And if we now start trying to run this, you'll see that the instruction pointer will just go round and round in circles as we run around the main idle loop, and it's waiting for something to happen. So what we'll do is we'll send it some characters. So if we set up the bits to suit what the HP 9845 would do, so in this case it's going to toggle a couple of the bits coming into the status latches, in particular this bit which comes through. If we scroll down, that is fed from IC1, and IC1 and IC2 are a couple of control lines from the 9845 processors that are used to select particular, we'll call them registers within external devices, in this case the printer. And by monitoring those bits, we can have the printer realize there's data waiting for it, and that's exactly how the actual hardware works. So we'll change this value so that it's now going to accept incoming data. The data comes in and it's on the let's pull the schematic up again. It's on this device. If we scroll up and across, it's coming through this pair of latches, and these are updated and read into the Nano processor as device 7. So what we can do is device input 7, we can enter the value of the character we want. This is in decimal, it's also inverted, so we have to invert the bits. This value, if you work it out, is for an uppercase A. So we're going to feed it an uppercase A. And so we don't just run off and have the software run into a loop indefinitely, we'll set an address. So I've gone through the software, and all this is going to do is stop on the line where it jumps out of the idle loop. If we now run this through, we'll stop as soon as we hit this address. Okay, I'll do this a few times, and each time around this loop it will input this data through the input buffer and latches, and it will write it into the RAM. So we'll see the data is now appearing in the RAM, and each time we go through the loop we'll see the data appear. Again, this is decimal, and this time it's not inverted, so this is now a value of 65, which is 41 hex, which is the value for an uppercase A. So although we feed it in as inverted data, it goes through the Nano processor input buffer, and it comes out as the correct data, and we need it to be true data because it goes straight from here to the shift registers. So we'll do this a few times, and you'll see that each time I go through the loop, the buffer, this is part of the RAM, is used to buffer the line of characters being sent from the HP 45. We'll change this to a B, so that's the value for a B. Send in a few Bs, do a C or two as well. So we've sent it a number of characters. They're now buffered in the RAM, and what we have to do now is send the control code. So it's just basically another character that's interpreted by the printer, and in this case we'll send it a value of 246. Again, it's inverted, and this will tell the printer to start printing the data that's just been sent. And so we'll run through one time. I'm going to set this value back to the idle value so it doesn't just keep running around in circles. And what we can now do is start this running. So I don't want it to keep stopping at this address, so we'll clear this and we'll run. So you can see now it's going through, and it's starting off by scanning the RAM. You also see that the motor is turning, and we're getting some data appearing in the shift register. So what I'm going to do now is put a value into the address halt box. So that's 1 BD, and this will stop us at the part of the code that is responsible for loading the character. You can see it's going to jump to a lookup table. We'll go through this, and each time it gets to this point, it's loading a value, in this case into the effectively into the shift registers that feed data out to the print head. Now the first line of characters, first line of data that's fed out is actually blank in all the characters, so it will just feed out zeros all the time. So what I'm going to do now is go through to an address in the code, so 1D4, and this is the part of the code that's responsible for shifting out the data. So what I'll do is I'll run this through. The first row of data is all zeros, so I'll run through until we start seeing some actual data, and then I'll halt it and we'll have a look to see what's going on. So you can see it's going through, scanning the data. We'll go right through the first row because there'll all be zeros coming out. Won't be very interesting to watch. I'll go on to notice the motor turn there. So it's now turned the paper, or turn the motor to feed the paper out to the next line. And it's now got to the point where it's starting to output some actual data bits. So we'll go back to the point in the code where it's loading that. We'll run till it stops. So it's now got to the point where it's going to try and load some data, and notice it's loaded the data. So this is part of the A character, and if we start stepping through this, you'll see the shift register, which has now been loaded with the data from the character ROM array, is going to start shifting this out. This small box on the right is the BSD line, that's the serial output line, and you'll see the data being shifted one bit at a time into that box. So shifted one bit to the right, another one, and this time we'll see a 1 appear in the output. There we go. And as we shift through, the rest of the bits will be shifted out, so we can be fairly confident that we've properly duplicated the functionality of the shift register. It can read data from the ROM, it can read data from the RAM, and it can read data from the nano processor. So this entire process takes quite a lot of clock cycles. We're now 236 milliseconds into the print. So what I'm going to do is allow it to run, and we can watch it outputting data to the printer so that we can actually see what's going on, because the actual data output part of the cycle is very brief with long delays between it, so we wouldn't really see much if we were to run at full speed. So what I've done is added an output panel, so this will show the data in the same form that the printer outputs data. Now this is not a simulation of effect or output. This is a simulation of how the data is handled within the printer, the Nano itself, and also the printer circuit. So this will form characters in the same way. So if we're getting characters here, which are essentially being formed by this bit being fed out onto each row, then we can be fairly confident that the overall system is working the way it should. So we'll start this running. It's going through, but it's, as I say, it's quite labour intensive, so it's fairly slow. So we'll run the system at 10 times speed, and we can watch, see what it does. You notice the motor turning between each line of pixels, and then the data should, in theory, start appearing on the printer output. This is really the paper reel on the printer. So we've got the first couple of rows of pixels there. It's going through, scanning the RAM, putting together the next row of pixels. That's now appeared, and you'll notice the motor turning between each row to feed the paper out. It's now doing the next. And remember, we output A's, B's and C's. That's the next one. Notice turning to the next line of pixels. It's going through the RAM again to see what characters are in which position, and then it looks up the correct byte in each bitmap, forms a line, outputs that. The long delay between each one is to not only feed out the paper, but also to allow the burn time to print the actual character on the thermal paper. That's why it takes so long. Most of this is delay. So as you can see, just a couple of rows left to do. Okay, so we're now, then it feeds the paper out again to give us a clear line. So it's now finished the print cycle. It's now just spinning round the, this is now the idle loop. And it will keep doing that now until more characters are sent from the HP 9845. But hopefully you can see that this is properly printing characters. It's doing it in exactly the same way that the printer hardware and the nano processor firmware are doing it. So this makes the basis for a very good tool. And what I can do, of course, as you can probably guess I've been doing already, is I can go through the system, find out which part of the code does which operation, and then focus on that area with the logic analyzer, rather than trying to figure out this very complex and convoluted sequence that would have to try and pick our way through if we didn't have this tool. And being able to just halt and run it gives us the best of both worlds. We've got the hardware we can refer to with a logic analyzer, and then we can analyze exactly what each part is doing in the simulator. And so I can really test them side by side, seeing how the hardware deviates from this simulation, and hopefully that will be a very quick and easy way of identifying where the fault is. So I hope you found this interesting. If you want to see more of this simulator, then leave a comment, but hopefully you can see it will make quite a useful tool.